In this video, we're going to look at asymmetry in photoemission peaks. The source for asymmetry is multifactorial, and one of the more significant factors in the shape of these photoemission peaks is the shape of the inelastically scattered background that is associated with the photoemission process. So this blue line represents the inelastically scattered background that has to be subtracted from the photoemission peaks so that we're left with what should be the photoemission signal that has undergone no scattering as a result of electrons moving through the sample. Then, in addition to the background signal, you also have the potential for loss processes to occur at the time of photoionization, but still these represent signal that arrive at the detector without undergoing scattering. So in some sense, all of these represent photoemission signal in a zero loss state. So we would like to model the shape of these peaks in order to work out the amount of signal we should attribute to each one of these peaks in particular. Now, in addition to the energy loss processes that are involved, there are also instrumental factors that influence the shape of peaks, and these are dependent on how an instrument has been set up and how a measurement is performed. But nevertheless, all of these factors are responsible for the shape that we see in these photoemission peaks, and any peak model that is aiming at collecting signal associated with zero loss processes must account for all of these factors when fitting peaks to data. When we measure photoemission peaks using synthetic line shapes, one of the important features of a line shape is that the area beneath that line shape, the functional form of the line shape that is, must integrate to a finite value. And that's exactly what a Gaussian does, it's exactly what a Lorentzian does. However, once you introduce asymmetry, that may not be the case. Now, while the functional form for a background may integrate to infinity quite happily, you can understand why that might be the case. In the case of a photoemission peak, we should be able to calculate an intensity that we can use in quantification. So an infinite area line shape is of little value when quantifying data by XPS. A commonly used line shape is the DS line shape. This is a line shape that was derived from theoretical basis for metallic materials, and the functional form looks like this, and it represents a peak-like structure and what I refer to as a step-like structure. And it's a step-like structure for alpha greater than 0. If alpha is equal to 0, then this whole thing reduces to a Lorentzian. So let's have a look at this in CasaXPS. And what I'll do now is I will use some of the features in the calculator to illustrate the DS line shape. I've prepared a VAMAS file that contains a synthetic spectrum which is derived from a Lorentzian. And then we'll look at the calculator, and on the calculator property page there's an option for using expressions. Now, I've previously placed within the VAMAS block comment some expressions that can be substituted into the calculator. So I'm going to select some of these and copy them, and then going to the calculator I bring up the expression dialog window. I've pasted into this an expression where I've got alpha, so this is the DS line shape alpha term. I've set it to 0.3, this is a value they used in the DS paper, and I've got the step-like term, and I've also got an asymptotic step-like term, meaning that I'm multiplying the abscissa by a large value so we can see what it looks like extended over a very long range. Here I just have from minus 60 to plus 60, so this is going to be multiplied up by a factor of 400. And then I have the peak-like structure here. So let's add these as expressions. So I'm going to start off by creating the product. So that's term 1 and term 2. And then let's put term 1 and let's put term 2, and let's then have what I've got is this asymptotic form. So the calculator will now substitute the value alpha in these expressions, the dollar in front of the 0 indicates we want not the intensities, but the energies that are associated with the intensities. So this is the x-axis, as opposed to looking at a calculation based on intensities of spectra. This is going to use the calculator as if it's simply creating these functional forms based on the energy range here. So these new spectra will be constructed by taking these forms after the substitutions have occurred for whatever is in these angle brackets. After pressing the OK button, the calculation is performed, and the first one was the product. So this is the DS line shape for a value of alpha equal to 0.3, and this has been constructed from these two terms. So this is the peak-like term that I referred to, and this is the step-like function, and this step-like function will always be above a certain value. And this is why the integral from 0 to minus infinity, the area in that portion of a DS line shape, is infinite. And that's why it's very difficult to make use of this when calculating intensities for XPS peaks. When the expression calculator is used to create a new VAMAS file containing VAMAS blocks that are the result of these calculations, then the VAMAS block comment includes the expression that was used to create these data. So this DS line shape is described here as a closed form. If I copy this closed form and then go to the components property page, having created a region, let's put a 0 background on this region, and then create a component. If the line shape is entered as CF, open bracket, a value, and then close bracket, the value represents a Gaussian, it's going to be convoluted with the expression that now is entered into the following space. When I press return, you can now see the line shape that has been created is based on the same expression that was used to create these data, especially if I now say fit, because you can now see that the line shape is identical to the data. So this is a way of prototyping line shapes. It might be useful to make use of the wide form for the parameters window so that you can see the full expression. The expression for this DS line shape can be replaced by DS 0.3, 0 and then return, and this represents the identical line shape in terms of shape. However, when you see the line shape, its position is different from the position that was defined by that closed form, and that's because the DS line shape is ensuring that when you have a Lorentzian based on the DS line shape, the full width half maximum for that Lorentzian will be unity, whereas in the case of the expression that's not true. So we need to then fit these data, and once you've pressed Ctrl G to fit the data, you can see that the fit is equally as good. It just means that the parameters have slightly different meanings depending on the line shape and how it's defined.